Good morning, everyone. So I'll present our paper, which title is Multi-Constraint Network Occupancy Optimization. So regarding the presentation outline, I'll briefly present the introduction, then I'll talk about system model, then I'll present our approach or algorithm, then I will continue with results, and finally end with discussion and conclusions. Regarding the introduction, I can say that increasingly different types of information are required in the system, which actually results in diverse and widespread use of networks. As the number of devices is increasing on networks, the network load and traffic is also increased. Although the network speeds are also increasing, it's always desirable to minimize the network load. One way by which the network load can be measured is network occupancy, which is actually amount of data that is passed through the network in a given amount of time. Because in the networks, there are multiple constraints. When we talk about network occupancy optimization, we must take these multiple constraints into account. So that's why we talk about multi-constraint optimization. It's not always easy to find an optimal solution. That's why we use heuristic algorithms that are based on human reasoning and thinking to find some optimal solutions. Regarding the problem formulation, this problem is motivated by the move from classic controller-centric to network-centric system. Here in the picture on the right, we have one network-centric system. It's consisted of input devices, which are sensors. On one side, on the low side, those can be directly connected to the bus, or can be connected first to the FCIs or field controller interfaces, which then group these signals and then forward them to the bus. On the other side of the bus are controllers, which have tasks which are, of course, run on those controllers. So the idea is to have a flow of signals from sensors to controllers and back. Each data set that is formed in FCIs has an ideal frequency by which the FCI assembles signals into that data set and packs them into packets. The goal here is, of course, to find the optimal packing schedule, to maximize the packet size utilization, and to minimize the number of packets. So we have kind of multiple objectives here so that the network occupancy is minimized. Regarding the contributions, first we determine a suitable optimization algorithm to solve this multi-constraint optimization problem. We, by the way, investigate how different packing methods can affect the reduction in network occupancy is network-centric models, and we study the impact of different network topologies on reducing the network occupancy in network-centric method. Some quick background. Generally, we focus on industrial networks, which are usually complex systems, and is desirable and the tendency to connect all devices in the industrial plants in the one network infrastructure. That's why we have network-centric systems in which all devices are logically connected to the same bus or to the same network, as shown here in the picture below. Ethernet is a network protocol or standard that is deployed and used. Among other things, it defines network speed, packet design, etc. And above that, we have an open platform communications, or a set of standards that defines secure and reliable interoperability of data in industrial networks and automation. It was a natural thing to model our problem as a bin packing problem. There are many variants of this problem, but generally one tries to fit a finite number of data into finite number of bins, so that the bins are so that the bin size is utilized as much as possible. It's heuristic methods here are often used to find a solution to this problem, and those can be roughly divided into online and offline. Online deal with signals as they come, while offline have all signals ready before actually before training or before running the algorithm. Our approach can be modeled as an offline packing algorithm. Regarding the related work, we consulted the literature in all of these four areas, I would say, but it was hard, at least to our knowledge, to find any paper or any literature that combines all these four areas, and that would give us some reference algorithm or something similar to compare with. Regarding the system model, we made some assumptions in order in order for our model to be ready for optimization. First, we focused on the part of the model between sensors and controllers. That is, we considered only one-way communication from inputs to outputs, actually. Sensors can only be connected to the bus via FCIs. So there's no direct connection between sensors and network. The time period in which the signal sends data is negligible. FCIs in every time moment has values from every signal in its registers, and the network is modeled as an ideal network. So there are no package losses, no collisions, no delays. Regarding the network package model, the term message is somewhat ambiguous, but because it can have multiple meanings in networks. Generally, we can say that network message, and that is the notation we use, is only the payload or the part of the network packet that contains data. But of course, by Ethernet standards, beside that payload, there are also various headers that define other information, like security information, etc. And it's important to know that within the field control interfaces, the entire package is created and sent to the appropriate controller. So we here on the left picture, we have an OPC package model of the package. We can see that in the second row, that's beside the payload, there are many other parts of the package which deals with security things and similar. But in our approach, we model the term package as a payload plus everything else that is in the OPC, and everything else we model as a header, which is of a fixed size. But payload is data set is signals plus sizes of those signals. On the right side, we can see some equations which define actually packets. First equation define the size of the packet as size of the header plus size of all signals that are in that package. A second is constrained on the maximum packet size, which is 1500 bytes. Third and fourth one define that at one time moment, one signal can be packed in only one package, so in one packing time. Regarding the system model, here on the right side is one simple network topology. We didn't use this topology for experiments, but it's only to show how we created topologies and numbered them. You can see the numbered areas; those are segments between controllers and switches, and switches and switches and switches. We didn't number and took into account segments between switches and FCIs, because as network is ideal, all data will eventually come from FCI to the nearest switch. There's nothing to optimize there. The destination of the signals is in one of the packages, and it is naturally to assume, because most of the data flows between switches, that these segments between switches will be most occupied. Regarding the occupancy, as I already mentioned, is actually amount of data that flows through part of the network in a given time interval. Here we measure time occupancy per segments. So network occupancy is actually the amount of data that flows through the segment in a given amount of time. And to actually get the network occupancy of the whole network, one just sums the network occupancies of the segments. As I said, some lines are expected to be more occupied than others. And also the network occupancy depends a lot on the relative position of the elements in the network topology. And it is naturally most affected by the frequency of the packages being sent or the number of packages and data through the network. Here we can see how one data set can be packed by naive approach that we took into account, because we didn't have any reference case to compare with. We had to create our own. So we took, I would say, some variation of next fits. So as we have one packet, as we have one data set, we go from the first to the last signal in that data set, and we just put them into the packets one by one. And we create as many packages as as must be created. So it's, of course, not very optimal, but that's the reference case that we use to compare with. But often all data intended for one controller or data that is one data set cannot fit into one package. So as you can see on the picture here, it can happen that packages are not fully utilized. Regarding our approach, possible improvements to this reference case are: we can consider merging data from different data sets into the same package, which could result in the higher network, in the higher package utilization, because the packing algorithm in the reference case leaves the packages unfilled. One interesting feature of task is they do not necessarily need the fresh or the newest values of signals every time they execute, so every period. That's why we introduce a parameter that's called number of allowed misses, or how many times a task doesn't have to receive or use the newest value of sensor data or a signal. And we'll see that it can tremendously reduce the network occupancy later. Regarding our algorithm, so in one FCI, based on ideal reading periods of all data sets, we can calculate a hyperperiod for that FCI. And in that hyperperiod, we actually can determine all time moments in which the packing will be done. And here, our algorithm consists of two stages. First is, in each time moment, determine all possible combinations of packing for different controllers in the same package, and then to perform bin packing algorithm to do the packing optimization, actually. Here we employed a best fit decreasing algorithm, but taking into account number of allowed misses for every combination we tested on. So here is just one small example. So if we have 3 data sets, which are intended for 3 different controllers, as shown in the table, with 3 different ideal reading periods, and they are packed in the same FCI. So we calculate the hyperperiod here, as you can see, and we determine the time moments in which all data sets will be packed. So we can create a timeline on this top right picture. And let's say we take the time moment of 300 milliseconds. Here we have 3 data sets that will be packed, and based on that we can create 5 combinations. So it's either try to pack all signals from all data set into one package, or one by one, or try to put 2 data sets into one package, and so on. And for every combination, we deploy BFD, so best fit decreasing, bin packing procedure, to actually to optimize the packing procedure. And then we calculate cost function, which is shown in the down left corner, which is actually defined as it's actually the network occupancy. So here PI is the size of the package I, which flows through the path LJ, and LJ is a path that connects multiple segments, of course. So we just sum that to get the network occupancy for every combination. Regarding the implementation detail, we use Python with object-oriented paradigm. Input and output data are actually in the form of Excel data sheets. And 2 parameters that are interesting for our simulations were execution time of 9 seconds, and it was for the data we created. It was actually the biggest hyperperiod of all hyperperiods of all FCIs. And this, we determined that the size of the package concept part or header is 33 bytes. We created 3 different topologies, and we tested our algorithm on those. And all of those topologies represented a variant of the medium-sized plant, of a network of a medium-sized plant, which and the number of devices defined by that medium-sized plant is shown here in the down on the slide. So here's the input data, how it looks. So actually on the left picture, it's important to know that every task has its task period, task execution time, and data sets of signals that is assigned to it. And every data set has a reading period. But you can see that these data sets are made so that they overlap a different tasks. Some of them, of course, not every. And on the right side, you can see signals with allowed repetitions or allowed misses, as we will name it later. And you can see here that we have 3 different sizes for signals. They correspond to 3 different types of signals which we used or which were given to us. Here's a first topology we created. That's just to show how it looks, how we numbered it. Other 2 topologies are just variants of this one by moving certain elements of network into other places. Regarding the results or output data, there are 2 representations. First one is to have network occupancy, which is achieved, which was measured by segments, and the total network occupancy as a sum of segments network occupancy. Here is important to note, as can be seen on this slide, that segments between switches are 4, 5, and 10. They are to be most occupied. And if one can see here in the table, in the top table, really those segments 4, 5, and 10 have the highest network occupancy on them. And the second table shows a packing schedule, which consists of time moments, and in every time moment we have number of packets that is created and that are created, and we have for every packet we have packet size and a list of signals that are packed. Regarding the results, first we investigate influence of different packing on network occupancy. Here shown one example from our results. Let's say we have 2 data sets with different ideal reading periods, and we calculate the reading period or the packing time in which they will be packed together, in which they will be packed at the same time. As one can see here in the reference case, 2 packets are created, and in our, as we call it here, optimal case, 1 packet is created. So one can see here, if one sums these packet sizes in the reference case, that there is the network occupancy in our proposed solution is reduced for 1 header size. But of course, given the number of packets and this sums, of course, and it's naturally to expect if a header size is bigger that there will be a bigger network reduction. Regarding the influence of different packing of network occupancy, here is just to show that just algorithmic-wise, relative network occupancy reduction is shown in the second column. So as you can see, it's relatively not very high, but given the volume of data in real networks, the absolute network occupancy can still be significant. But when we take into account these parameters of allowed misses, one can see that a significant, tremendous network occupancy, around 67% network occupancy reduction, is achieved. Regarding the influence of BFD algorithm on package utilization, here we see the case where, given the reference algorithm and our proposed solution, the same number of packets are created. But one can see that in our proposed solution, 3 packets are fully utilized, while in the reference case only 1 packet is utilized. Here we show our proposed approach actually creates more packets that are fully or more utilized regarding their maximum size. And in the second column, we can see how the number of allowed misses affects the packing. So we can see roughly that Without allowed misses, signals in the last column are actually repeated at every time moment they are sent. But when we take allowed misses into account, one can see that signals are not sent in every time moment regarding their allowed misses parameter value. So one can see that in 150 and 225 milliseconds, there's a big reduction in the number of signals that are sent and packed, which of course reduces network occupancy. Here is to show that the influence of topology on network occupancy. So moving from topology 1 to topology 2, we can see that we achieved a reduction in the segments 4 and 10. Here we show only segments 4, 5, and 10 because those are most occupied, and it was the primary goal to optimize or minimize the occupancy of those segments. So we can see the reduction in segments 4 and 10, but we can actually see that segment 5 occupancy of that segment is higher than in the topology 2. So that is a trade-off that must be taken into account. It's hard to achieve to reduce network occupancy on all segments, but if the reduction is higher or in absolute size bigger than on some segments, then it is an increase. In other segments, it's still doable. And we can see in topology 3, when it's related to topology 2, that we achieved 0 or positive network reduction in all segments. We did it by actually moving controller nodes closer to the switch nodes, or switches, controllers and nodes closer to the source node. But as source nodes are related to switches, that's actually moving them closer to the switches. Now, to conclude, we actually propose a heuristic approach for addressing this multi-constraint network occupancy optimization. We use the best fit decreasing algorithm, but we added this type of allowed misses into account, I would say. And we show that merging data sets into the same packets has actually shows a reduction in the network occupancy. And also network occupancy, as I already mentioned, can be significantly reduced by bringing the end nodes or controllers closer to the source node, or FCIs in our case. Regarding the future work, of course, we can consider the communication from end nodes to source nodes. That is both-way communication, or to have both-way communication from source nodes to end nodes and vice versa. We can include jittering calculations in a way that we don't have an ideal reading period, but we have a jitter time interval around that ideal reading period, in which reading and packing and sending can be done. So of course, it will make a problem harder to model, but of course it will model a real network better. And we can, of course, model a more real model of the network to have data collisions, data loss, and happen. And we have the propagation time taken into account, because we here say that the propagation time is negligible. Thank you very much for your time and attention. Here's the GitHub link to our code if anyone is interested, and of course, questions now. Please feel free to ask. Thank you.
Okay, thank you, Amar, for your presentation. We have a few minutes for the questions. So please, if you have some questions, just unmute yourself and ask.
Yes, maybe just a short question from my side. So this is a centralized algorithm, if I understood well. And in reality, you have a distributed system. So this packing will take place in the different points in the network. So whether you consider developing the distributed version of your algorithm, do you see any problems in that?
Well, yeah, to be honest, we didn't think into that direction, but given your question,
I think it's very important, because now you're just considered theoretically this, and this is the first step, of course. But then to transfer it into the real project, you next natural step would be to make a distributed algorithm.
Yes. The problem, I don't know, maybe there can be, because when we choose or when we create the combinations of packing, before we apply a bin packing algorithm, we do take all combinations into account. So that's a bit like an exhaustive search. So actually, to reduce the computation time, maybe in the distributed system, one can only select, using some algorithm, a number of those combinations to test.
Exactly, yes,
Yeah.
along these lines somehow. Okay, thank you.
Yeah, thank you too.
Okay, next question. Jeff, Sam? Okay, I wanted also to ask, because you mentioned that it's the system where you have some communication, you have these sensors and controllers interconnected, and you mentioned that probably this will be the Ethernet connection, so some protocol running over Ethernet technology. And I wonder whether you also consider some other constraints, because what I understood was that you try to pack or to combine different readings that you want to transfer to the controllers into a single packet. So not to send a lot of small packets or frames, but to send rather bigger frames, which is better for utilization, of course. And what about some time constraints? So what if I want at the control to read the value, and if I read it later, it's useless for me. So I need to say, okay, I cannot pack this reading with some later reading because I need this value at some precise moment. So is it also somehow considered, or just you don't care because your reading is, let's say, so often and repeated so fast that if you miss one reading at the controller, it doesn't matter for your system? Or
yeah,
how hard a real-time system you consider in your work?
Well, we consider more or less a very ideal version, I would say. So I think we mentioned in the paper that the controllers in their registers have in every time moment a signal ready for every task in such a way. So yeah, it was idealized.
Your reading is just updating some local register with a new value. So
Yes.
if you just have this signal a little bit later, it doesn't matter for your task.
Yes, and yeah, I also mentioned that everything is ideal, so no losses. So everything is assumed to be on time, to get there on time.
We can add also, I mean, as Amar presented, that you saw that we are allowed to skip some samples. So that comes to your interpretation of, or to your question about real time. So we kind of may skip sending those samples that are not necessary at some moment. I mean, absolutely necessary. And then, of course, some other ones you cannot drop the information at the specified times. However, yes, this could be affected later. I mean, as future work should be analyzed also, as Amar said, by problems of the network losing packages and so on.
Okay, thank you for.
Yes, but I think that Andre wanted to make a point about end-to-end deadlines. Sometimes in hard real-time systems we have them, and so it's important.
Yeah, that's why you have this repetition, and that's how you basically get. This is an input information. Yeah, so this is something that you know already, that you have to send those packages at those moments of time. Yeah, so it may happen that some given these moments of time, some of them you may not send because it's not necessary, but those that are selected in the work, then means you have to send them.
Okay.
All right.
Maybe one last, just for my clarification. So at this moment, your work doesn't consider like some timing or time-related issues. So your goal was to somehow reduce the number of packets or the number of bytes that you need to send on the links between the switches that interconnects all the different parts, because as you mentioned in the motivation, the bottleneck is something that may be a problem for the system.
Yes, as this was, at least to our knowledge, a very novel problem. This was like the first idea to go with this. So we didn't consider anything timing related.
Perfect. Very nice. Thank you.
Yeah, thank you.